Hi, and welcome to this quick review of electrophilic substitution reactions. Make sure you've got the relevant independent study materials and notes with you while you're playing the clip. And what we'll do is look at the mechanism itself in general and briefly go into a range of common A-level electrophiles and reactions. So in the examples above, what I've done is I've placed the positive charge on the specific atom in the electrophile which actually substitutes onto the ring. So in the general mechanism below, all of the above electrophiles can be considered to be the same as A+. So let's go through the steps. So the first thing to make sure you do is you have the curly arrow touching the actual ring in the benzene ring, the circle, which represents the delocalized pi system. So this first step creates a partially delocalized pi system with 4 electrons present. So the positive charge is shifted into the partially delocalized pi system containing 4 electrons. So 2 electrons from the carbon-hydrogen bond are attracted into the pi system, restoring its quota of 6 electrons. This breaks the carbon-hydrogen bond, releasing the hydrogen as H+. So you're left with a fully restored delocalized pi system with electrophile A that we started with substituted onto the ring. And the positive charge hasn't disappeared, it simply has been transferred onto the hydrogen that's been lost as H+. So let's have a look at what you need to take care of when you're doing the mechanism. So the curly arrow must start at the ring itself and point at the electrophile. It's the carbon-hydrogen bond breaking, so start the curly arrow there. The arrow points at the open end of the partially delocalized pi system. The line represents where the U shape of the partially delocalized pi system should stop, as there's 5 carbons still involved in it, which I've now highlighted. And the carbon atom where substitution has taken place should be clearly bonded to the atom on the electrophile which carries the positive charge. So if you look back up at the electrophiles towards the top of the screen, you'll see I've highlighted where the bonding takes place. It's the actual positive charged part of the electrophile that bonds directly to the carbon that's highlighted on the mechanism. It's very important to get that bit right. So for each of the electrophilic substitution reactions that you need to know about, you need to know what the electrophile is, how it's created using a catalyst or an equation, what the catalyst is, what its identity is, what the reaction conditions are, and how the catalyst is regenerated, again using an equation. So if we start with the nitro group, notice I'm keeping the positive charge on the nitrogen because that is the atom that carries the positive charge. So the equation is basically a nitrating mixture which forms the electrophile plus HSO4 minus plus H2O. And if you're drawing out the equation, it's fine to put the plus charge next to the oxygen. The catalyst is your H2SO4 and the reaction conditions have to be 50 to 55 degrees C, refluxed with both acids concentrated. Very important to get all those details down. And finally, the H plus from that was originally on the benzene that the NO2 has substituted for is recombined with HSO4 minus to make H2SO4, which is your catalyst. So moving on to the bromonium ion or bromine ion. Notice I didn't say bromide ion. It's Br+. You have AlBr3, which is a catalyst, and this is called a halogen carrier. So what it does is it produces the Br+ electrophile for you. Now you could also use FeBr3 or indeed iron as a solid metal mixed with bromine as a liquid, which would obviously produce FeBr3, as is illustrated by the equation there. So you can obviously use other halogen carriers according to the halogen that you're actually trying to substitute. So you could use AlCl3, you could use AlI3, etc., or even AlF3. So the reaction conditions are room temperature and pressure. And once more, the hydrogen ion that came off the ring during substitution plays a role here and reacts with the AlBr4- to produce HCl and release AlBr3, or regenerate the catalyst. So in the case of alkylation and acylation, which I've colour-coded, you can see that what we do is we use a chlorinated species. And we react with this chlorinated compound with the halogen carrier. In this case, it's AlCl3 in both examples with the same reaction conditions and the same equation for regenerating the catalyst at the end. So hopefully you found this a reasonably useful sort of roundup of all the different types of catalysts and reaction conditions and electrophiles you're likely to come across when studying electrophilic substitution reactions at A-level. So as always, there's no substitute for going and practicing some question examples now. So until next time, thanks a lot for listening and see you soon.